Alright, so last time we talked a little bit about base excitation. We looked at what happened when we have one mass and one base, and then there is some input from the base. In this case we saw that mathematically, of course, we have a little bit more to look at, because the equation of motion looks different, especially from the right hand side, because we have the input and then we have the velocity, so the effect of that comes from the effect of the dashpot, sorry. And then we saw that we said actually that in order to solve these equations, this type of equations, we have to look at a slightly different form. We didn't go too much in the details on this because I wanted to focus more on the final result. We can have the steady state solution in this form, so this term multiplied by the cosine of this term. We can introduce again the frequency ratio. When we introduce the frequency ratio, we look at the transmissibility ratio, which is this quantity here, so the ratio between the amplitude of the displacement of the mass and the amplitude of the displacement of the input. When we look at this quantity here as a function of R, our frequency ratio, we see something very interesting, because we see something that looks like this here. And we said that there are two parameters two values that we need to look at. One is the value of the frequency ratio 1, where we see, sorry, it's a little bit out of focus. Let me adjust. You can't see it. Okay, I think I need to share the screen. Alright. Are we good now? Okay, thank you very much. So we said that when we look at the transmissibility ratio or displacement ratio, this is how the function looks like. So when the frequency ratio is equal to 1, we can still see an increase of the amplitude, but also another value that we have to look at is this square root of 2, because when R is lower than square root of 2, the input of the amplitude of the input is amplified. On the other hand, when the frequency ratio is greater than square root of 2, we have actually a decrease of the amplitude of the displacement. So this is something that is very useful when we want to work on devices that need to actually dissipate by external vibrations, because in that case we want to design our system so that the natural frequency is greater than, so the ratio between the natural frequency and the frequency of excitation is greater than this value here, this square root of 2. Make sense? Any question about what we saw last time? Alright, if there are no questions, we can move forward, and that was a kind of, how to say, transition between what we had before, which means we were looking at a single degree of freedom systems, to what we are going to see now, which are 2 degree of freedom systems. So before we start to look at the equations, before we start to look at derivations, calculations, there are a few important concepts that I want to highlight. And in particular, I want to talk about the main differences between single degree of freedom and multiple, and let's say 2 degree of freedom systems, and in general multiple degree of freedom systems. So the very first difference is that when we look at a single degree of freedom system, we look at one natural frequency. We saw that this parameter for example, a simple harmonic oscillator is given by the ratio between, the square root of the ratio between k and m. We saw that if the system is a little bit different, we can find some way to determine through the equation of motion the natural frequency, but we always end up with one value of the natural frequency. This is because we have been dealing with single degree of freedom systems. Now that we are going to work with multiple degree of freedom systems, we will have multiple natural frequencies. So we will have one natural frequency, we will have as many natural frequencies as many degrees of freedom. So if we have 2 degrees of freedom, we will have 2 natural frequencies. Another very important aspect is that so far, working with 1 degree of freedom, single degree of freedom systems, we worked with 1 variable. Even in this case, we have we can have different situations. We can have horizontal displacement, we can have a vertical displacement, we can have a rotation, for example. Or if we have multiple displacements, we have always been able to correlate all of them to each other, and we ended up with only 1 variable to look at. In this case, when we move from single to multiple degree of freedom, we also need to expand the number of variables that we will look at. Because once we work with multiple degree of freedom systems, it means that we work with systems that have multiple bodies, for example, that can move independently from each other. So since they move independently from each other, and we will see very soon an example, we cannot correlate the 2 variables, the 2 displacements, for example, which means that we have multiple variables to look at. Makes sense so far? Another very important thing, another consequence, is that so far we have been trying to find the equation of motion of the system. From now on, we will not deal with 1 equation of motion, but we will deal with multiple equations of motion. Because the equation of motion, when we were working with single degree of freedom, basically was telling us what's going on to our single variable, to our displacement, and then by looking at that equation of motion, we were able to determine what was going on with that displacement. Now that we have more than 1 displacements to look at, we will also need more ways to describe all these displacements, which means mathematically we need more equations of motion. Another very important aspect is that when we look at these multiple equations of motion, the hard part is that these equations of motion are not independent from each other. So even if, I would say that even if the variables are independent to each other, the equations that describe the motion of these particles or these bodies are coupled to each other, which means that we end up with systems of equations that must be solved all at the same time. We cannot take 1 single equation out of this system and solve that independently from the other equation. And this is what makes multiple degrees of freedom systems more complex than single degree of freedom systems. However, we will go probably next week through some way to make our life a little bit easier, which means we will work with model analysis, and the model analysis will allow us to actually separate all the equations, make them independent from each other, so that we will be able to solve all of them one by one. But this is something that we will see later. The last thing that I want to mention as an introduction to multiple degrees of freedom system is that, as we just said, we will work with systems of equations, and since we work with systems of equation, we will need to use matrices to describe our system instead of using like a linear form of equations. All right. Any question so far? Alright, now we can start to look at the most simple, probably, example of a multiple degree of freedom system, and of course we will start with 2 degrees of freedom. So let's assume that we have a situation like this, where we have one mass that we can call M1 and another mass that we can call M2. So we can have one spring between mass 1 and the wall and another spring between mass 1 and mass 2. So we can also call them K1 and K2. Now, is this a 2 degree of freedom system? Yes, it is, because in order to fully describe what's going on this system, we need 2 variables. The first variable is the displacement in the horizontal direction of mass M1, which will be our x1, and the second variable will be the displacement in the horizontal direction of mass M2, which will be x2. Now, this is just an example of 2 degree of freedom system. We can have a situation, for example, where we have only one mass, but still 2 degrees of freedom. For example, we can have a situation where, let's say, I don't know, we have one mass, that is connected to the ceiling and to the wall. In this case, the same mass can move in the horizontal direction and in the vertical direction. So looking at the number of masses for a discrete system is not enough to determine how many degrees of freedom we have, because in a case like this we can have one mass but 2 degrees of freedom. Makes sense? Also, another example could be, for example, a car. If you look at what's going on a car, let's assume, I'm going to try to do a schematic of a car. So if we have the wheel, the other wheel, let's assume that the body of the car is connected to the wheels through the suspension, to the 2 suspensions. So in this case we can have 2 degrees of freedom, because we can have the motion of the whole body in the vertical direction, but if the 2 springs are either stretched or contracted in a different from a different amount, we will also have a rotation of this body here. So if the 2 masses go up and down by the same amount, we have 1 degree of freedom because the mass can go up and down. But if they are squeezed or extended by a different amount, it means we have also rotation in this direction, which means that we have still 1 mass, 1 body, but 2 degrees of freedom. Make sense? So again, let's pay attention when we look at how many degrees of freedom we have. Okay, let's go back to our simple situation. The steps that we are supposed to follow are actually the same that we have been following so far. We just need to extend what we had from 1 single degree of freedom to more than 1 degree of freedom. So what should we do first? In order to find the equations of motion and then the solutions of these equations of motion. What should we do first? We should do the force balance for each mass, which means we have to look at the free body diagram, right? So we can start from the first mass, M1. So we have 1 force in this direction. So even in this case, we assume that the motion occurs in the positive direction for both of them. So if the mass m1 is moving towards right, it means that the spring is stretched, so the spring is pulling back. So this we can call this K1 x1, right? On the other hand, for the other spring, because we have another spring, we have also the force that in this case depends on the elastic constant of spring 2, but it depends also on the difference between the displacement of x2 and the displacement of x1. Remember, this is the same thing that we said when we were talking about the base excitation. If in that case the mass and the base move by the same amount up and down, it means that the spring doesn't bring any force because it's not stretched or contracted. So what we should use to determine how much force comes from the spring to the mass is the difference of displacement between the two masses. So we have x2 minus x1. We can, of course, we have the force in the vertical direction, which would be like the gravity and the normal force, but they are balanced, so we can ignore them. This is what's going on for mass m1. We need to look at mass m2 as well. So in this case, what kind of force do we have in the horizontal direction? In this case, we have only the force from spring K2. So which means that we can look at the force, and even in this case, of course, this force must be equal and opposite to this force here. So we'll have K2, and since we already included like the direction, the opposite direction, we'll have x2 minus x1. So now that we have the free body diagram of mass 1 and mass 2, we can use our summation of forces equal to m x double dot. And of course we have to apply this twice. We have to apply to the first mass, the second mass. So for the first mass we have summation of forces equal to m1 x1 double dot. So the force, of course, we have to pay attention to the directions now. So we have negative K1 x1 plus K2 x2 minus x1 equal to m1 x1 double dot. So we can rearrange so that we will have all the variables of interest in evidence. So basically what we obtain is m1 x1 double dot plus k1 plus k2 times x1 minus k2 x2 equal to 0. So this one so these two terms go on the other side. So we have k1 x1 becomes positive, so it's here k1 x1, k2 x2 becomes negative on the other side, so here negative sign, and then this k2 x1 here is negative, becomes positive, so it's k2 x1. Let's do the same with the second mass. So we have summation of forces equal to m2 x2 double dot. This is slightly easier because we have only basically one force here. So we have negative k2 x2 minus x1, which is equal to m2 x2 double dot. Also in this case we can rearrange, so we have m2 x2 double dot minus k2 x1 plus k2 x2 equal to 0. Any questions so far? So now we have our system of equations where we can relate what's going on with the first mass, because we have our first variable x1 and also x1 double dot, and what's going on with the second mass, which is x2. So here we have x2 and x2 double dot. So now we can order a little bit more these two equations. So the system, so it's a little bit easier to see when they are together, becomes m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to 0, and then the second equation is m2 x2 double dot minus k2 x1 plus k2 x2 equal to 0. Again, these two equations are coupled because both variables x1 and x2 show up in both equations. Make sense? So now, as we said before, since we start to deal with systems of equations, we can write them in matrix form. So if we write them in this one in matrix form, this is how it becomes: m1 0 0 m2, and then we have, this is x1 double dot x2 double dot plus k1 plus k2, and then we have negative k2, and then we also have negative k2. Here we have positive k2, and then here we have x1 and x2 equal to 0 and 0. So I want to give you 1 minute to kind of reflect and compare what we have here with what we have here. Any question on how to go from here to here? So if we write our equation in this way, in a matrix form, it is very similar actually to what we had at the very beginning when we were looking at the simple harmonic oscillator, because in that case we had m x double dot plus kx equal to 0. I'm going to write that again. In that case, again, for a single degree of freedom, just to recall, we had m x double dot plus kx equal to 0. This is again for single degree of freedom. So this was, I think, the very first equation of motion that we found this semester. So, but if we look at this one, the two forms are actually very similar to each other, because here we have one matrix that multiplies one vector. This matrix contains the masses, and here we have the mass that multiplies the acceleration, plus another matrix that contains all the stiffnesses of the springs, multiplied by another vector that contains the displacement, which is basically the same thing that we have here. So we can write this one, again, in a more general form as m times x. I'm going to use, these big letters, mx double dot, to indicate that these are matrices and vectors, plus k x equal to 0. So this m from now on will be the mass matrix, this x double dot of course will be the acceleration vector, then we will have this big K, which is the stiffness matrix, and then we have this vector here, excuse me, this is the x double dot, the acceleration vector, so that here, this one, will be of course the displacement vector. So when we work with, any questions so far? Okay, so when we work with 2 degrees of freedom, or in general multiple degrees of freedom systems, and we want to write the equations of motion in a matrix form, so once we obtain the matrices, this is a very good point to stop for a second, because we can make the first check to kind of figure out if we are in the right path to obtain the correct form of the equation of motion. So what do we have to do? We have to look at these 2 matrices, the mass matrix and the stiffness matrix. So what do we have to check? We have to check that these 2 matrices are symmetric. Symmetric means that when we look at the principal diagonal, whatever we have above and below must be symmetric. Which means in this case, when we look at the principal diagonal m1, m2, above here we have 0, here we also have 0, so it means this is a symmetric matrix. Same thing is valid for here. We can have pretty much whatever we want on the principal diagonal, but above and below the matrix must be symmetric, and this is the case as well, because here we have negative k2 and here we also have negative k2. So again, when we go through these steps, once we are here, if our matrices are symmetric, very good chance that our calculations so far are correct. Make sense? So now what we should do, we should look at the solution of this equation. We can call as a single equation of motion because we wrote in a matrix form, but we know that this comes from multiple, in this case 2 equations of motion. So the solution of this equation will also be a vector with 2 elements, and the 2 elements of this vector, of course, are the displacement of the first mass and the displacement of the second mass, so x1 and x2. So, but we can keep using this matrix form, so we can write the solution as a certain coefficient that we can call like bu in this case, times e to the power of j omega t. So this is a big U, or an uppercase U. And then times e to the power of j omega t. Of course, this again, this is a vector, which means it has two elements, x1 and x2. U, this big U, is also a vector that has two values, u1 and u2, and we will see later how we can use this u1 and u2. But for now, what we should focus on is are these two elements, this u and omega. These are basically our constants that we have to determine from this general form of the solution. How can we determine these two? We can do something similar to what we did before, which means that we can derive these twice, then we can plug in our general form of the equation, and then from there we can see what kind of result we obtain. So when we derive the first time, we obtain x dot, which will be equal to j omega times u times e to the power of j omega t. We can derive one more time, so that we obtain x double dot. So we derive one more time, we obtain j omega, which is this constant here, times u, which is the other constant. And then we have to derive this one, which means we have again j omega times e to the power of j omega t. Can we simplify this a little bit? Yes, we can, because here we have j and j. If we multiply j by itself, we obtain -1, because by definition is the square root of -1, so this will be, again, j times j is -1. Omega times omega becomes omega square, so we have negative omega square u times e j to the power of j omega t. So now that we have our second derivative and the function, the general form, we can take actually this one, and we can plug them here. So what we have is m, again this is the mass matrix, negative omega squared u times e to the power of j omega t plus k, which is this k here, times x, which is what we have here, so u e to the power of j omega t equal to 0. We can put together this term here, u e to the power of j omega t, and it means that we are left with minus omega square m plus k times this term here. Let me write it down. So we have negative omega square m plus k that multiplies u e j omega t equal to 0. Now from this equation here, this is a product between basically three quantities. The first quantity is what we have here between parentheses. The second quantity is our displacement, our vector that basically will be the amplitude of displacement, and then we have this term here. So if we want that this function is equal to 0, this term here, e j omega t, will never be 0, is an exponential. Also u cannot be 0, because if this is 0 we have the trivial solution, So the only way to have this quantity equal to 0 is to have the quantity between parentheses equal to 0. So from here, what we obtain is that negative omega square m plus k equal to 0. Remember that this is an algebraic, is a matrix equation because both m and k are matrices. So what we have to do in order to solve this one is to, again, consider these two as matrices, which means that what we need is to determine the determinant of this matrix here, negative omega square m plus k equal to 0. So for this one, we already have M, the mass matrix, which is what we found here. We also have K, which is a stiffness matrix that is here. So we can solve this equation here. So I want to give you a couple of minutes to plug these two matrices, to practice a little bit here, and then let's see what we obtain. So what we should do here is to, again, as I mentioned before, simply plug what we have from the previous page in terms of mass and stiffness matrices. So basically we have omega square, negative omega square, that multiply the mass matrix, which is M1, 0, 0, M2, plus K, which is stiffness matrix, which is K1 plus K2, negative K2, also negative K2, and K2 here. So we make these calculations. We simply need to multiply omega square by M1 and M2 here. So we have negative omega square M1, 0, 0, negative omega square M2, plus, I'm not gonna rewrite again the stiffness matrix, but what we have here is the same what we have here. And then we have to add the terms that are in the same row and same column. So we have to add this one to this one, so we will have negative omega square M1 plus K1 plus K2, and then we have to add this one to this one, so we have negative K2, and then we have to add this one to this one, so we also have negative K2, and then here we have to add this one to this one, so we have negative omega square M2 times K2. So what we have to do, we have to equate the determinant of this 2 by 2 matrix, which is, okay, we can do this. Yeah, we can do this. This is typically what we do when we have bigger matrices. So we get rid of either one column and one row. In this case, since we have the 2 by 2, we can go straight to the product between the quantities on the principal diagonal and then the product of the quantities on the other diagonal. So which means that the determinant of this matrix is equal to the product between these two minus the product between these two. Right. So the product between these two will be simply, we can rewrite omega square M1 plus K1 plus K2 times negative omega square M2 plus K2 minus the product between these two is plus K2 squared, but we have the negative here, so it becomes K2 squared equal to 0. So what we should do now, we should multiply, all the terms. Here we have 3 terms, here we have 2, so we will end up with these 6 terms. And then we have, of course, we still have this K2. We can rearrange all the terms. So after a couple of steps, again, just very basic algebraic steps, this is what we should obtain. Omega to the power of 4, that multiplies m1, m2, minus omega squared, that multiplies m1, k2, plus k1, m2, plus k2, m2, plus k1, k2 equal to 0. So here, this is a very important equation, because this is the characteristic equation or frequency equation for the system. As you can see here, the unknown that we have, assuming that of course we know the parameters of the system, which are basically the masses and the springs, the unknown in this equation is actually this term here, omega. So we said that when we have more than 1 degrees of freedom, so for example in this case we have 2 degrees of freedom, we will have 2 natural frequencies. Those 2 natural frequencies will be found from this equation here. When we were working with 1 degree of freedom, we were looking at the equation of motion, and from the equation of motion we were able to look at the coefficient of x, and from the coefficient of x we found the natural frequency. In this case, what we have to do, we have to look still at the equation of motion in matrix form, and then once we have the mass matrix and the stiffness matrix, we can go through these steps, and then we find this equation. Again, this is a characteristic equation. From the characteristic equation we can find the natural frequencies. Make sense? I would expect a question now. Any question? Yeah. We are supposed, so the question is, are we supposed to have 2 natural frequencies? Yes, we are. If we look at this equation here, this is a 4th order equation, which means that from here we will obtain 4 solutions. However, since it is like a quadratic equation where we have like omega to the power of 4 and here omega to the power of 2, basically what we will obtain are 2 couples of solutions. One will be plus or minus a certain number, the other one will be plus or minus the other number, pretty much. So when we look at this, of course we are not going to consider the negative value of the frequency, because physically we are going to look only at the positive value of the natural frequency. So out of those 4 solutions, 2 positive and 2 negative, we are going to look only at the positive solutions. Make sense? So that's why eventually we end up with only 2 natural frequencies. Very good question. The other thing that we should look at when we solve this equation is that we should basically sort our solutions in order. So we will have always that omega 1 is smaller than omega 2, smaller than omega 3, smaller than omega 4, and so on. So the first, even if we will see that we have to pay attention, because even if we find the first natural frequency, the second natural frequency, and then if we expand the third, the fourth, this doesn't mean that the first mass oscillates with the first natural frequency and the second mass oscillates with the second natural frequency. Because basically these are natural frequencies of the system, and basically all the masses together oscillates at all natural frequencies, because these are coupled. And we will see from, I don't know if today we will have chance, but for sure next time we will see from the final solution, where on the displacement of the first mass you will see both omega 1 and omega 2, and on the displacement of the second mass you will see both omega 1 and omega 2. Makes sense? So now I would say we can, now that we have this, which is again the frequency equation or characteristic equation, we can actually do an example. We can try to put some number, because now the equation even symbolically become a little bit big. So we can try to put some numbers and let's see what happens when we put numbers. So we can have put numbers for masses and stiffnesses. So what I have here is M1 equal to 9 kilograms, then we have M2 equal to 1 kilogram, then we have K1 equal to 24 Newton per meter, and then K2 equal to F3 Newton per meter. So what I want you to do, you can use these values here, 9, 1, 24 and 3, to find the natural frequencies of this system here.